This is work that I did with my advisor, Michael Scott, at the University of Rochester. And I just got a job this fall at Houghton College, and I'm teaching there, but I welcome the opportunity to abandon my students after the first week and come and talk with you. Feel free to ask questions as we go along. I'm happy to sort of answer as we go along. I don't want anybody to sort of get left behind. So this work is about improving the performance of software transactional memory, and with an idea that we had that we call transactional structs. I'll give a little overview of how the Haskell STM works sort of internally in the runtime system, and a little bit of the road and the long journey to getting tstruct working, and a little bit more detail of an example of the difficulties that we have implementing this, and also how it works out kind of practically, and then the performance results from adding this feature. So what is transactional memory? It's two ideas put together. Instead of expressing how things should be atomic, just express the things that need to be atomic. And then an implementation that uses speculation to execute those atomic blocks. Haskell adds on top of that a couple of other interesting ideas with retry and or else. And those things aren't particularly important to this work, other than we support those features fully. So the Haskell implementation has these transactional variables that are sort of distinct from everything else, and that makes sense in the Haskell context. And each transactional variable holds a single pointer to a heap object. When a Haskell transaction executes, it reads and writes. The reads and writes to the transactional variables don't actually happen in the actual transactional variable heap objects, but instead are tracked in this transactional record. Only the initial read does anything to the transactional variable, which is to read the value that it sees then. And then it continues under the assumption that there aren't any conflicts. This is called a lazy software transactional memory, which is fitting for Haskell. At the end of the transaction, the runtime system will validate that all of the reads that happened along the way, those values are still the values that are in the transactional variables. And it will then atomically commit all of the writes. But that atomically extends not just to the writes, but to observing the reads having the right value. So it's a little bit tricky, especially to get a fine-grained implementation. So historically, the implementation comes from Kara Fraser and Simon Harris's work with OSTM, and it has the properties that there's no global bottleneck, which is really nice for good concurrency, and read-only transactions don't end up acquiring any locks. That's great. OSTM goes a little bit further and is non-blocking. GHC's STM probably could be extended there without any major trouble, but its current implementation does have a little narrow window for live block. So what's our motivation then? When you only have one value in your transactional variable, you end up having a lot of different indirections. So if I want to make a data structure for a red-black tree, each individual node is going to look like this, where each one of these boxes is a separate heap object. And I have to follow all of these pointers if I want to get to the color of a particular node. And the color in a red-black tree is just one bit of information. So there's quite a bit of overhead to storing and accessing this color. So the idea is simply make this sort of heap object representation for the whole node at once. We call that a transactional structure, a tstruct. So we're saving a lot. We're also sort of combining all of the STM metadata from the multiple transactional variables that were in the TVAR version, one for each mutable field, into just one kind of chunk of STM metadata. And that's a choice that we want to explore in the future of the granularity of the metadata for the transactions as we go along. But notice we have word fields where that color is, one word, and then we have 3 pointer fields for the structure of the tree. So why should this help? Well, I'm a systems person, and we know that memory is really the big thing to think about when you want performance, and concurrent and parallel programs are especially sensitive to memory accesses and the performance, and we know a lot about why that is because of the way that we design hardware. So improving locality is a good idea in general, and using less memory is also a good idea. Working with unboxed values, these are all good ideas. They should help, right? So it should be easy. Just implement this structure and get faster programs. So the first problem is OSTM critically requires that the lock and the value field are the same field in the transactional variable. And if we're going to have unboxed values, we can't do that. And if we're going to have multiple values, we can't do that. So we have to figure out a way to implement something OSTM-like, but not have that conflated lock and value. So after lots of head scratching and trying to do this, we found that if we combine the lock field and the version field, there's a version field so you can sort of detect any changes that happen between that initial validation of the reads and the acquiring of the locks to write all of the values for the updates. If we combine that version field and the lock field, we can do a similar effect of having the other two combined, and that we can atomically get both the version and the lock value. So we had to think about lots of different interesting interleavings of all these transactions at the bottom, sort of flipping X and Y back and forth. And as our transaction executes, we observe in between those transitions back and forth. And we observe the same strange transition when we validate. So we have to make sure that we can catch that in the read check. And so this is an example from Fraser's original OSTM that we had to think about in a different way in the context of the version number conflated with the lock variable. And it ends up to work out. Sort of more complicated examples that we had to think of, and details of what this picture means are in the paper. So that sorted out, what else could be a problem? And it turns out that writing code that avoids allocation is kind of hard and error prone in Haskell. And I made it a little bit worse by using that. I don't need to say much more about that. And fragile code is hard to refactor. So the sort of cycle of I'm just going to kind of refine my benchmark is hard to do, and it breaks constantly. It's my own fault, right? I used unsafe coerce. Unsafe coerce sharp, the kind one. So we had to develop a little bit of tools to sort of help us. So we instrumented the runtime system to tell us interesting information like how many allocations are happening inside a transaction. And it's not a perfect instrument, but we were able to use that to sort of focus in and run like a read-only workload and see how that affected allocations, and really kind of narrow down where in the code to focus on working. And that was really helpful. And just as a, in the end, we did successfully achieve what we hoped. T-Struct reduced the amount of allocation in transactions and reduced the total memory footprint of the data structure. So that wasn't the case with the first round of code that we wrote. We had to go through a long refinement process to get there. So example of that, if we have a red-black tree and we want to know what the color is, well, just sort of naively, I make a distinguished nil object. I don't get to use some types with tstruct, unfortunately, so I have to do something. So I make a nil, and then I have to add all these checks for nil all over the place. But that's not so bad. It's just a branch, right? It turns out writing code like that causes more allocation, not just a branch. So if I change it, which maybe I should have written this in the first place, and have that nil always be black, then I can just use the read color directly. And that reduced allocation significantly. So there are surprises. So after we sort out all of those surprises, are we good? No performance gain after all of that. Oh, what's the problem? Transactions per second are the same for tvar and tstruct, even though we know we've reduced the allocation. So what's wrong? Well, if we look a little bit deeper, transactions per second of mutator time is greater for tstruct. So we've lost our time to the garbage collector. And we looked into it more, and it looks like long-lived objects are staying in the first generation. And there's this choice in GHC that we just copied naively, that mutable objects are not subject to eager promotion. And I think that makes sense in the right context, but this is not the context where that makes sense. So we fixed that, and now we get the same GC time. So our performance increases quite a bit. So a little bit longer example here. One of our data structures is the hash array map tree. And in the tvar version, we have lots of extra indirection. And in the tstruct version, we have a couple of things that we have to overcome in the code that we write. One is, how do we initialize one of these transactional structures? It's hard to do that without a little bit of unsafety. I don't want to spend the overhead of transactionally initializing something that nobody else could possibly see. So I want to do some unsafe accesses to those nodes. I also want to have some fields that are immutable fields, in which case I don't want to pay the overhead of using transactional access, keeping it in the transactional record. And giving that feature is quite error-prone. And I don't have some types, because that would add an indirection. So I need to have a tag field, and I need to have the code kind of properly handle that. So these immutable fields, we just expose an interface that lets us non-transactionally access things. But that's really dangerous, right? If anybody uses that in the wrong place, things could go terribly wrong, and in very unexpected ways. For instance, if you non-transactionally read a field and that value ends up being used in a choice as to whether or not you call retry, and that actually was a mutable field, then your retry may never wake you up because it's not tracked by the system. You don't know what dependency you have in that transaction. So it's very dangerous. And in fact, the kind of most obvious way that this happens is you want to have a random number generator. Non-determinacy is already part of concurrency, so it seems pretty reasonable to non-transactionally access the random number generator, but it could go wrong. So the tvar version looks like this. We have a nice sum type for the different kinds of nodes in the hashed array map tree. And each node has this sort of wide fan out that's a compressed array and a bitmap that tells you which bit indices are actually set in the array. And then leaves are just collection of collisions. And you hash your key and then follow down the tree. And, oops. The tstruct version conceptually is the top thing. We throw away the sort of non-transactional single leaf optimization. Conceptually, we just have two forms, the nodes form and the leaves form. And they both have a very similar shape. But in the real implementation, we're just going to do like the bottom one there with just a tstruct. And we know that the different fields have different meanings. So in pictures, we go from all of these indirections to something nice and compressed. So what's the code look like? To do a lookup, in the tvar one, we access the tvar, and then we can do pattern matching like normal, and write our programs pretty much like we would expect Haskell programs. In the tstruct version, we build up a little bit of an API for accessing things and give meanings to particular fields. So there's a constant there of the 0th index in the word part of the tstruct is going to mean the tag, so that we can simulate sum types. And the lookup thing is going to read the tag, and then we just have that 0 there. I'm sure we could all come up with better ways to do this that have a little bit more type safety, but I just want to get the good result. So lots of error-prone things. So, but thinking about it, we have a good idea for how to fix that with Simon Marlowe's Immutable Fields extension, extending on top of that and adding STM as a possible kind of target for these mutable fields. So you can declare data types and mark certain fields as mutable, and also mark a context in which the data type makes sense. So this one makes sense in STM. And all the accesses will have to be through the STM monad. And now when we go to look up, we can pattern match on this because it's a sum type. But internally, it's still that sort of nice compressed heap object. And we access the fields. When we pattern match, we don't get the value in the field, but instead we get a reference to the field. And we can dereference that inside STM. So it works out really nicely. I'm working on the implementation. It's not done yet, but I'm very excited in how many problems it solves. It solves a lot of the issues. We can get the sum types. We have the that sort of pure leaf one. We can introduce that back in without any problems. And it just solves a lot of issues. There's also a lot of potential for extending it to solve other issues like the initialization problem. We can do something like an ST version that we can freeze into an STM version. So the results, we had 4 data structures, and we had a big machine with lots of cores, and we combined them together, and this is what came out. So for the hash array map tree, we have a couple of other friends here too that are good comparison points. So first, the tvar version is the thin blue line, and we can see that our version, the tstruct, the black line, is kind of pairing it, but with better performance. And then the next one, the C tree, that is a concurrent lock-free version of the hash array map tree where the updates are done with a compare and swap, and you would expect it to get pretty good performance, and it does. It can't do what tstruct can do in composability, in that if I have two data structures and I want to atomically access both of them, the tstruct one and the tvar version can do that. The C3 one can't do that. Yeah. Yep. And then the pure tvar version is just a single tvar with a pure data structure underneath. The unordered containers, I think it's hash map or just map, I don't remember. But it's a hash array map tree, the same data structure, but a pure functional version. And you can see that it doesn't really get any performance benefit from multiple threads because of that kind of bottleneck of the single transactional variable. You can do a little bit better with a little bit smarter atomicity operation with the pure CAS, which uses Ryan Newton's atomic modify IORef CAS. And it can't, you can't combine data structures and retain atomicity, but it doesn't get really good performance until you sort of hit that wall of high contention. And we hit that as soon as we go to the second socket in this case. So there are 18 cores on the first socket, and then we fill up the second socket, and then we go into hyperthreads, which are generally not useful here, but in other data structures, they do help. So the Cuckoo Hash version, we get really good performance with also. And you can see, especially as we get out into the hyperthreads where memory contention is more important, because your level 1 cache sort of gets divided in half with your contending hyperthread. And skip lists, we just generally do better as well. Red-black tree, we marginally do better, and only sort of at the end. The one thing that we want to play with the red-black tree is playing with the granularity of that STM metadata. It may be that we're too coarse in this instance, because if you're updating colors up the tree, that's going to cause conflicts with readers that are going down another branch. So that's unfortunate, and that may be why we don't get as good a performance here. So in the future, I'm going to keep looking at how we can improve performance. I'm going to continue with my implementation of the Immutable Fields extension and explore that. There's lots of interesting implications for a lot of concurrent data structures and other things. And look for other data structures and real-world programs that use concurrent data structures. So, thank you. Sorry, what? Well, it involves lots of modification to GHC to get it to work. So eventually, what I see happening is when a good story is out there for mutable fields, then it will include tstruct in its implementation. So in some future version of GHC, I definitely hope to have it in there. Yes.
You mentioned that there's a little window in which you could be bypassing that, but there are other things you need to clean up.
Yeah.
Did you find things that you could just straightforwardly improve?
Yes. Yes, there are lots of things. And I hope to. I hope to. But I do have to get back to my students at Hogan, so. Yeah, and the version is really,
I just want to make sure it's not solved about it.
yeah. There's lots of ways that you can do transactional memory. The real benefit of the version is in this recheck section, and it's the mechanism in order to tell whether or not the values that you saw, it's not enough to just check and see if all the values are the same, because you could have seen the same inconsistency later on. And seeing that same inconsistency is detected by the version number. Yeah.
When we see throughput graphs like that in Haskell, I guess one question always, I know we talked about the garbage collection.
Yeah.
But what were typical productivity in the left, middle, and right of the graph on those scalability tests?
That's a good question.
Scalability, is it because the speed or is it because?
I don't know that off of hand because the version of GHC that I was working with for a long time, I'm pretty convinced was lying to me about the productivity numbers. So I stopped looking at them, but that's something that would be really good to look at. I think they remain pretty good. But I've also played with the sort of like initial heap size and things like that to sort of find interesting things like that.
I forgot, what was the instruction mix? What percentage right is that?
Very low. 5% end up actually writing. It's 10% writes, but half of those are the expectation of not finding the deletion. Mm-hmm. Unbox sums. I have only briefly sort of looked at that, so I haven't dived into that particular feature. That's a good question.